I want to show you a super handy way you can use your equilibrium equations to find out how much weight is on each end of a beam. And remember, your equilibrium equations are about a thing that is not moving. It's in equilibrium, so all the forces add up to zero, all the forces in the x direction and the y direction, and all the moments add up to zero. And you'll recall that for every action there's an equal and opposite reaction. In this case, in other words, the sum of all the forces in the y direction have to add up to zero. The force coming down, the reactions pushing up. And you'll recall that the load might be centered, and so you have an equal reaction on each end, or the load might be off-center, and so you'll have a different reaction on each end. So let us think about a couple of examples here. I made this a trailer so you could think about figuring out how much load is on each axle, let's say. And in this example, you have a beam that weighs 200 pounds, and you have a box on top of the beam that weighs 400 pounds. And the box is in the center of the beam, and the beam is all uniform, so its weight is centered too. Everything is centered. So, what is the total weight in this arrow that represents the load up on top? Well, you would add the 400 pounds and the 200 pounds, and you would get 600 pounds. So the load on top of this beam, including the beam, is 600 pounds. What about the reactions? Well, we know that the sum of all forces in the y direction add up to zero. We know we've got 600 pounds coming down, and that means that the reactions at A and B pushing up also are 600 pounds. And because this thing is centered, it must be that the reactions at A and B are equal. And if they add up to 600 altogether, it must be that each one of them is 300. Now let's think about a beam where the weight is off-center. In this one, we have a beam which weighs 500 pounds, and we have a box on top of it which weighs 800 pounds. So the weight of the beam is centered because it is. The weight of the box, however, is off-center. It's 20 feet over on a 30-foot beam. So we could draw a free body diagram of that trailer with the box. And here's what it looks like at the bottom of this slide. A free body diagram pulls the beam free of everything that's touching it. It just shows the beam, and arrows for the forces and arrows for the reactions. There's a free body diagram of this trailer, and it includes dimensions for where those forces are located. Now, can we put the weights on those arrows? Well, we've got 500 pounds that's centered right here, so that arrow with the that's centered at 15 feet over must be 500 pounds. And then we can put the 800 pounds on the arrow that's 20 feet over. So there's our free body diagram with the weights on it. Now you rummage around in your toolbox. And almost always, the tool that you are going to pull out when you start figuring out the weights on a beam is the sum of all moments equals zero. So let's do that. The reason we need that is because we have two unknown reactions here, and if we did sum of all forces in the y direction, we've got two unknowns. We don't have enough information to figure it out. But with moments, we can. If we take moments around one of the reaction points, around point A, let's take moments around point A in order to find how big the reaction is at B. So A will be our pivot point. And let's think about what direction these moments are going to go. These two weights, the weight of the beam and the weight of the box, are each trying to rotate clockwise, so they will each be a negative moment. And they're rotating around point A, that's our pivot point. And then the pushing up reaction at B is trying to rotate around A in a counterclockwise direction, so that's going to be a positive moment. All right then. Now let's start doing our tool, our equilibrium equation. Sum of all moments around A equals 0. And by the way, how do we know they equal 0? Because this thing is not moving. Just a reminder that the formula for moment is force times distance. So we're going to be working our way across left to right, going force times distance, force times distance, force times distance. Let's do that. So the sum of all moments around point A is, first we have the negative moment from 500 pounds times 15 feet. See, here's 15 feet from A over to that force. Then we've got a negative moment caused by 800 pounds from a 20-foot distance from the pivot point perpendicular to the line of action. And what else have we got? We've got the reaction at B. B's causing a positive moment because it's going counterclockwise. We don't know how big B is, but we do know the distance. It's 30 feet from A to B. There we go. And what do these add up to? They add up to 0. So we can begin combining some of these numbers. 500 times 15 is 7,500. 800 times 20 is 16,000. B times 30. I'm just going to write 30B because I like that better. It's more an algebra sort of form. Okay? So we got that. We can push these two numbers together now using our friend the calculator. So those two numbers together add up to negative 23,500. And we've still got the positive 30B. And they still add up to 0. So let's try to get B by itself. Well, first of all, we could add 23,500 to each side. Move that 23,500 over here. Now it's a positive number. And now we've got 30B by itself. Yay. And now we can divide both sides by 30. And that gives us, because the 30s cancel out, B equals 783 1/3 pounds. If you like to think about unit analysis, notice that we've been doing foot-pounds, foot-pounds, foot-pounds. When we divided both sides by 30, that 30 is a measure in feet. So we've got foot-pounds divided by feet. Foot-pounds divided by feet. The feet cancel out and we're left with pounds. So B has a reaction of 783 1/3, or another way of thinking about that is the weight on this front axle is 783 1/3 pounds. Now let's figure out how much weight is on A. Now looking in our toolbox again, we could do sum of all moments again if we wanted to, but now that we know what B is, it will be faster if we do sum of all forces in the y direction equals 0. So let's do that, because we only have one unknown here. How do we know this thing is in equilibrium? Because it is not moving. So that means all the forces in the y direction add up to 0. And what have we got? We've got A pushing up. Now we're not thinking about moments anymore. We're just thinking about forces in the y direction. So when we're thinking about y, positive y is up, so A is pointing up. Then we've got 500 pounds coming down, so that's a negative 500 pounds. We've got 800 pounds coming down, so that's a negative 800. And we've got 783 1/3 going up, so that's positive. So there's what we've got. And what does that add up to? It equals 0. So there's our equation. Now let's smush these three numbers together, which you could do with your friend the calculator. Minus 500 minus 800 positive 783 1/3. And you come up with this number, negative 516 2/3. A minus that equals 0. So now we can just add 516 2/3 to both sides. You'll wind up with a positive number over here on the right. These two cancel out, of course. And we're left with A equals 516 2/3 pounds. So we can write that on our free body diagram. And now we know all the weights. We know the weight on each axle, and we did it using the equilibrium equations. Sum of all moments equals 0, and sum of all forces in the y direction equals 0. And you can use this method all the time. If you're designing a deck on a house and you've got more weight off center, you want to figure out how much weight is on each post, you can do it. If you're designing something with a trailer, you can figure out the weights on the axles. If you're doing a building and you want the weight on each wall, it's the same method. So if I were you, well, I'll tell you what I would do. I would take notes. I would write this down on pieces of paper, and I would kind of keep that as my cookbook to refer to anytime I need to figure out weights. So there you are. You've got the secret now.